Let's do some more implicit differentiation. This time, let's do it with trig. So what I can do here, I can distribute the x. I don't think it makes my life that much easier though, so I'm going to keep it undistributed. So I'm going to derive both sides with respect to x. The derivative of sine with respect to x, the variables agree, so this one's easy, just cosine x is equal to, and then here we're going to have to use the product rule. So we have f and we have g. F dg, so the derivative of the second function, plus g df, derivative of x. Cosine x equals x times the derivative of 1 is 0 plus the derivative of tangent of y. Remember that y is a function of x, and so we have to use the chain rule. Well, let's remember the chain rule. The derivative of tangent u, tangent of a function, is secant squared u times u prime, the derivative of u, or the derivative of the inside. So this one will be secant squared y times y prime, or another way, in the way we've been writing y prime, is dy dx. Plus, and then the derivative of x is just 1, so we get 1 plus tangent y times 1. Continue to simplify, 0 plus, so this is just all one term, x secant squared y times dy dx plus 1 plus tangent y. We want to isolate the dy dx term, so subtract 1 and subtract tangent y on both sides. So on the left side you have cosine x minus tangent y minus 1 is equal to x secant squared dx dy dx. And it's already factored out. It's only attached to one term, so now we do our last step of dividing x secant squared x on both sides. And the derivative of y with respect to x would be this fraction. Find dy dx implicitly for the equation sine of y equals x. Then find the largest interval of the form y between negative a and a, on which y is differentiable. Y is a differentiable function of x. We will begin by deriving each side with respect to x. The variables do not agree here, so we must use the chain rule. The derivative of sine of y, a function of x, is cosine of y times the derivative of the function within the argument, which would be dy dx, equals the derivative with respect to x of x, and that's 1. Our step here is cosine y, and you dividing cosine y, and you get dy dx is equal to 1 over cosine y. They said find the largest interval in this form on which y is differentiable. Okay, so let's take a look at this graph. There are several largest intervals, okay? You could go from here to here, and that's a function. Once you curve right back over, though, you fail the vertical line test. Because it just keeps going on forever, we're going to choose the interval closest to the origin. And remember that it needs to be in this form, negative a to a, the restrictions for what y can be. So the interval around the origin is right about here. this is actually the same restricted piece as inverse sine, right? Remember when we reflected sine over the line y equals x? Then we got this reflected version of sine, which is not a function unless you restrict it. And the y values, the range values for that restriction, if you remember, were negative pi halves to pi halves. And the domain was from negative 1 to 1. So here we have a zoomed in version of that section. We found the interval for which y is a differentiable function of x. Is there a way that you can write this derivative explicitly so that y is not a part of your dy dx derivative? To do that, we need to remind ourselves of any special relationships that we have found thus far or been given. And the special relationship I know is that sine of y is equal to x, but I don't have sine of y. I have cosine of y. So is there a relationship for which I could possibly get this cosine y to be some quantity with sine in it instead of cosine? Because if it's sine y, then I can replace it with x. And you know what? There is. It's called the Pythagorean Identity. Sine squared y is what we will call it in our case, because we're dealing with cosine y and sine y. Sine squared y plus cosine squared y is equal to 1. And we're going to solve for cosine y. So subtract sine squared y on both sides, square root both sides. Cosine y is equal to plus or minus the square root of 1 minus sine squared y. But which one do I replace it with? Do I put positive root 1 minus sine squared y? Do I put negative root 1 minus sine squared y? Do I even know what the values of cosine y are giving me? Yes, I do. All the tangent lines in this interval, besides of course the edge ones which are vertical, all of these tangent lines are positive. They all have a positive slope. So because we chose an interval for which y was between negative a, and we're working with sine y equals x, then cosine y is giving me all positive outputs. So cosine y cannot be plus or minus square root 1 minus sine squared y. It is only positive square root 1 minus sine squared y. Again, this is still with these restrictions. Now I have a value of sine squared y, but I don't know sine squared y. Or do I? We have sine of y. If sine of y is equal to x, then sine squared y, squaring that entire side, would give me that entire side squared, x squared. Now we replace sine squared y with x squared to get an explicit differentiation. To write our derivative explicitly, meaning we need to have x's only in it, not y's, then we would write 1 over, instead of cosine y, we can now replace it with its equivalent expression, square root 1 minus x squared. Now that we've written it explicitly, we do not need to write its restrictions. Our restrictions helped us to figure out which version to use, plus or minus. In our interval, the results were only positive. So the final answer does not need to state any restrictions because they're basically embedded into this explicit form. What if they're asking you to find the second derivative with implicit differentiation? This is a little different than regular higher order derivatives, second, third, fourth derivatives with just regular differentiation, okay, you're going to want to keep track of any special relationships that they give you or that you come up with in the process. For example, x squared plus y squared equals 25. That is the first relationship they've given us, and then they've asked us to find the second derivative of y with respect to x. That is what this notation means. All right, so we will derive this implicitly. You could also solve for y, but it's going to be easier like this, I believe. The derivative of x squared is just 2x. The derivative of y squared, y is a function of x. That is 2 times y to the 1 times the derivative of the inside, which is the derivative of y with respect to x, is equal to 0. Get dy dx by itself by subtracting 2x on both sides, and then you'll divide by 2y. When we reduce, we get negative x over y. Ding, ding, ding. Now you have found another special relationship, the first derivative. Guess what? We're going to do it again. We're going to use the quotient rule. So I'm going to leave this negative in front, and then low d high minus high d low over low squared we go. Low d high minus high d low, derivative with respect to x of y, or dy dx over low squared y squared. And this negative is in front of the whole fraction, so if you end up distributing it, it will go to all the pieces in the numerator or denominator, but not both. So the derivative of x is 1. This would be y minus x times the derivative of y with respect to x over y squared. Well, dy dx, we actually know what that is. We have a relationship. It's negative x over y. So we will begin by replacing that. That's why it's important to keep track of your relationships. Negative x over y, all over y squared. Take a little bit of time to combine these and really simplify. So I multiplied this by y over y, so it would have the same denominator. So this is y squared, negative in front of the whole thing, y squared over y minus, so negative times a negative is a plus, so plus x squared over y, all of it being over y squared. Remember that this whole thing is negative, so I'll write it as negative y squared plus x squared over y. So I combine the top, and then I'm going to multiply it by the reciprocal of the denominator. So instead of dividing by y squared over 1, I'm going to multiply by 1 over y squared. Negative y squared plus x squared over y cubed. At our final step, we look and see if there are any other special relationships that we could substitute in to simplify this further. And if you notice, x squared plus y squared is equal to 25. So I can actually simplify the second derivative to be negative and then replace this quantity with its equivalent, which is 25, over y cubed. Always check for additional simplifications based on the relationships that you have kept track of while you're doing the problem. Find the tangent line to the graph given this equation and this point. First of all, I think distributing will make my life easier, so x to the fourth plus x squared y squared is equal to y squared. Now I will take the derivative with respect to x of both sides of this equation. The derivative of x to the fourth is 4x cubed plus this will require the product rule. So I will write it as derivative of x squared times y squared, and then derive it in the next step. And the derivative of y squared is 2y times dy dx. Remember, that is requiring the chain rule because the variables do not agree. 4x cubed plus, this will be f and this will be g. So f dg plus g df equals 2y dy dx. Okay, derivative of y squared. We already did that, didn't we? It's 2y dy dx. So x squared times 2y dy dx plus the derivative of x squared is just 2x, so y squared times 2x equals 2y dy dx. I want to group all my dy dx terms on the left side, and then I'll bring the other terms to the right side. So we have x squared, we'll call that 2x squared y dy dx, this term right here, and then subtracting via inverse operations equals negative 4x cubed minus this term 2xy squared. I will factor out the dy dx. So 2x squared y minus 2y equals, and then I would like to factor out anything here. So I factored out a negative 2x squared plus y squared. We'll divide both sides by this quantity, and when I divide it, when I write this down, I'm going to actually factor it as well. Save myself a little bit of writing, so take out a 2y, and you get x squared minus 1. This is just a special form of the number 1. So dy dx is equal to, and now we can reduce, 2 over 2 is 1, so you have negative x times 2x squared plus y squared over x squared minus 1 over y times x squared minus 1. The original problem asked us to find the equation of the tangent line at the point root 2 over 2 comma root 2 over 2. So for x and y, we will replace root 2 over 2 in the derivative. Root 2 over 2 over root 2 over 2 is just a special form of the number 1, so the numerator will still be negative, but you have root 2 over 2 being squared a lot. What is root 2 over 2 times root 2 over 2? That is 2 over 4, which is 1/2. So this is, so every single one of these is just equal to 1/2. We have 2 times 1/2 plus 1/2 over 1/2 minus 1. I'll write 1 as 2/2. So negative 2/2 plus 1/2 over, what's 1/2 minus 2/2? That's negative 1/2. Negative over negative is a positive. So now we have in the numerator 3/2 over 1/2, which is 3/2 times 2, which is 3. Woo! That is our slope. We still need to find the equation of the tangent line. So the slope is 3, and the point is root 2 over 2, root 2 over 2. So plug that into y equals mx plus b and solve for b. So root 2 over 2 is equal to the slope, 3, times root 2 over 2 plus b. So root 2 over 2 equals 3 root 2 over 2 plus b. Subtract 3 root 2 over 2. B is equal to 1 root 2 over 2 minus 3 root 2 over 2 is negative 2 root 2 over 2. 2 over 2 is 1. B is negative root 2. So what's the equation of the line that has the slope 3 and the y-intercept negative root 2? Y equals 3x minus root 2. This equation shows us a famous curve called the kappa curve. And here's the line we found the equation of the tangent for.